The two concepts we're going to cover in section 1.4 are symmetry and midpoint. The first concept, symmetry, you've seen before. Most of you are familiar with the term symmetric and which figures are symmetric. If we look at the heart figure, we can see that this heart is symmetric. The left side and the right side are mirror images of each other. This type of symmetry is called line symmetry or reflection symmetry. If a figure has line symmetry or reflection symmetry, to describe that symmetry, we count the number of lines of symmetry. In this example, the heart has one line of symmetry. In the second example, the hexagon also has line symmetry. To describe the line symmetry, we need to count the number of lines of symmetry. The hexagon has 1, 2, 3, 4, 5, 6 lines of symmetry. The third example, the sun, also has line symmetry. Draw in the lines of symmetry. How many lines of symmetry does the sun have? We can count them. 1, 2, 3, 4, 5, 6, 7, 8 lines of symmetry. Other figures are also symmetric, but they don't have line symmetry. If we look at our first example here, this figure does have symmetry, just not line symmetry. It has another kind of symmetry. The type of symmetry that this figure has is called rotational symmetry. If I take this figure and I rotate it, it will coincide, it will line back up with itself. And I can keep rotating it around and it will line back up with itself. This type of symmetry is called rotational symmetry. To describe a figure with rotational symmetry, we're going to use degrees. How many degrees can we rotate that figure until it lines up back with itself? If I spin the figure around this center point, how many degrees will it take for this line to line up right here? Well, there's a couple ways I can figure out that angle. I can take a protractor and measure it, or I can see that it's going to take 3 rotations to get all the way around. And there's 360 degrees in a circle, so 360 divided by 3 is 120 degrees. I could go another 120 degrees for a grand total of 240 degrees, or I could go another 120 degrees and end up with 360 degrees. So this figure has rotational symmetry at 120 degrees, 240 degrees, and 360 degrees. Our second figure also has rotational symmetry, but no line symmetry. To figure out the rotational symmetry, I figure out how far the object would have to be rotated until it lines back up with itself. If I draw this line in, I would have to rotate the object to this line. Again, I can use a protractor to measure that angle, or I can keep going all the way around and see that I can rotate this figure 6 times before I get all the way around. Again, 360 divided by 6 is 60 degrees. This figure has rotational symmetry every 60 degrees. I'm just going to count by 60 degrees. 60 degrees, 120 degrees, 180 degrees, 240 degrees, 300 degrees, 360 degrees. This example down here is one of my favorites. If you look, it says rotational symmetry. And if you take rotational symmetry and you rotate rotational symmetry, it lines back up with itself and says rotational symmetry. To describe that rotational symmetry, I need to figure out how many degrees I rotated my figure before it lined back up with itself. If this is the center point of this figure, I had to rotate 180 degrees, and then I could rotate another 180 degrees to get back to the center, or to get back to the original. So this figure has rotational symmetry every 180 degrees. A figure can have both line symmetry and rotational symmetry. If you look at this last figure, this square has line symmetry. In fact, it has 4 lines of symmetry. The square also has rotational symmetry. But be careful, I can't just say, well, from here to here is 45 degrees, so this square has rotational symmetry every 45 degrees. If I only rotate the square 45 degrees, it won't coincide, it won't line up with itself. I need to rotate 90 degrees. So this square has line symmetry every 90 degrees. Notice I'm just counting by 90 degrees. So a figure can have both rotational and line symmetry, like the square. It can have just rotational symmetry. Or if you look at our original heart, our heart had just one line of symmetry and no rotational symmetry. The second concept we're going to cover is midpoint. Midpoint is just the point in the middle of a line segment. The directions for this problem say draw in segments AC and BD. I'm going to take a ruler and I'm going to draw in the segment AC. I start at point A and I end at point C. To draw in line segment BD, I'm going to start at point B and end at point D. Again, use a straight edge and connect those points. Both line segment AC and BD have a midpoint. It's the point that's halfway between AC and the point that's halfway between BD. The question is, what are those two midpoints? Well, if you look, we are on a coordinate system. To find the midpoint on a coordinate system, we're going to use the midpoint formula. The midpoint formula is going to give us an ordered pair answer. Our answer is going to be in the form x, y. To figure out our x values, we're going to find the value halfway between our x's. To find halfway, we're going to average our two x values. To average them, we're going to add our x's together and divide by 2. To find our y value, we're going to find the y value halfway between our two given y values. To find that y value, we're going to average our y's. So if I want to find the midpoint of segment AC in a coordinate system, I'm going to first label my points x1, y1, x2, y2, and plug those values into my midpoint formula. x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. Now I need to do that math. -3 plus 1 gives me -2. 8 plus -1 gives me 7. Keep simplifying. -2 divided by 2 is -1, and 7 divided by 2 is 3.5. So the midpoint of AC is at the ordered pair -1, 3.5. I'm going to start at the origin, -1 in my x direction, and 1, 2, 3.5 in my y direction. Notice that the midpoint is halfway between A and C. The distance from A to the midpoint is the same as the distance from C to the midpoint. To find the midpoint of BD, I'm going to also want to use the midpoint formula. I'm going to label my points x1, y1, x2, y2. And now I need to plug those values into my midpoint formula. x1, x2, y1, y2, and do the math. 3 plus -1 is 2. 8 plus -1 is 7. Simplifying my answer, I end up with 1 and 3.5. So the midpoint of BD is at 1, 2, 3.5. Ultimately, the question is asked, are the two midpoints the same? My final answer is no. In order to get that answer, I need to show all my work. I need to use that midpoint formula to find those midpoints to decide if the midpoints are the same or not.